All right, so today we're going to look at some indifference formulas, and the first sets of formulas, you have them on your sheet. What they do is they show you what you can do with values that are either added angles or subtracted angles. So when we were looking at angles back in Chapter 2, there are some angles that we really like. They're on the unit circle. We know values for them. 30 degrees, 60 degrees, 45 degrees, 122, 10. We can talk about radians, right? We talk about pi over 3s and pi over 4s and pi over 6s. Those kinds of angles were all friendly angles because we memorized the unit circle, right? But if I gave you pi over 5, you would be stymied as to what to do, and the best you could do would be to approximate it with a calculator from last chapter, correct? All right. These formulas give us tools to be able to work with and find values exactly when we can take the values and express them as two values that are added together. So let me show you an example of what I mean by that. And we're going to work in degrees first because we're a little bit more comfortable with that. 105 is not a value on your unit circle. However, you can write it as the sum of two values on your unit circle that you do know and you do like. What two numbers add up to 105? 45 and 60. So I could rewrite this as the cosine, and it doesn't matter the order. Okay, so 45 degrees plus 60 degrees, or 60 plus 45. Everybody with me? And then I can use that identity that was just on the previous slide. In fact, it's the very first one that tells me what I can do when I have two angles added. And the way that I can separate them out is, in this case, alpha is my first angle. We wrote that down as 45. And beta is my second angle. We wrote that down as 60. So this formula tells me that I can write this as cosine of 45 degrees, cosine of 60 degrees, minus sine of 45 degrees, sine of 60 degrees. And all four of those are values you know from the unit circle, or you should know. Okay? So what is cosine of 45 degrees? Radical 2 over 2. What is the cosine of 60 degrees? 1 over 2. Good job. 1/2. What is the sine of 45 degrees? Square root 2 over 2. And what is the sine of 60 degrees? Square root 3 over 2. Now here's a nice feature for you. When you're working with these, okay, for sine and cosine anyway, tangent's a little bit different, but for sine and cosine, when we combine them like this, they're always going to have the same denominator. That's very friendly, okay? So no common denominator finding. We've already got it. So this is square root 2 over 4, right? Minus what? It is square root of 6 over 4. And the best we can do to combine these is to write them as square root 2 minus square root 6 over 4. Please do not think that you can simplify that square root 2 and that square root 6 and somehow put them all underneath one square root. That is absolutely not a property of square roots, okay? However, I want you to realize that you can check this solution too, right? What could you do to make sure you got the right thing? You bet. The first piece can go straight in your calculator, make sure you're in degrees, right? You can take cosine 150 degrees and it will spit you out an approximation. And then you can do the same thing with the solution we just found out, right? You can type in, be careful with your parentheses, square root 2 minus square root of 6 and either press enter and then divide by 4 or put the whole thing in the top in parentheses and divide by 4. And you'll get the same approximation. Great, right? Yeah, it's nice. It allows us to change things. Now, we're going to work with another one in radians. Okay. So anytime we've got something over 12, it's often really nice. And the reason it's really nice is because think about the pi over whatever's on your unit circle. We have things over 2, 4, 3, 6, and all of those are factors of 12, aren't they? So anytime we've got a denominator of 12, that's actually a very friendly denominator, even though it doesn't look like it right now. So we need to think about, and you can do it with subtraction as well as with addition, but my mind tends towards addition usually first, and addition will work here. Two different angles that will add up to 19 pi over 12. I just cheated, so. Do you want to know what they are? Okay, but you guys know how you can play with it and try and find out, right? Okay, you just take your calculator and you add a couple of the fractions together and see if they end up with 19 over 12. Okay, 5 over 6 and 3 over 4 work. Okay, so whoops, let's try that again. So we can rewrite this as tangent of 5 pi over 6 plus 3 pi over 4. The tangent formula is a little bit more cumbersome to work with. Okay, so let me show you what's going to happen. We've got tangent of 5 pi over 6 plus tangent of 3 pi over 4. That's just using the formula. We're just writing down from the formula right now.
So you're,
Was it subtraction? Did I write it wrong?
no, so your sign, never mind, makes sense.
Are we okay, Alex?
Yes.
Okay.
It's addition.
Yeah.
When you do subtraction.
Yeah, and then the denominator is actually 1 minus, and it has a negative in that denominator. Yes, Maikia?
Okay, 19 pi over 12, that's supposed to equal 5 pi over 6 plus 3 pi over
I sure hope so. I didn't check it when I got to the final steps like I just told you just a minute ago you could. Can somebody check it for me? Can you add it? Does? Oh, somebody said it did. So apparently, yes, it does, Maikia. Thank goodness, because otherwise we're sort of up creek. All right, so we've got the tangent 3 pi over 4 over here. The easiest way to check, Maikia, if you wanted to check, is to take 5 over 6 plus 3 over 4 and hit enter, and then do the same thing with 19 over 12 and hit enter and see that they are the same decimal approximation. Okay, tangent is also a value that's it's more difficult to work with because it's not just the x or the y on the unit circle, so it just flat out is more difficult to work with. So let's take a moment and remember what each of these are, and I'm going to write them over here to the side. Tangent of 5 pi over 6 takes the sine value over the cosine value at 5 pi over 6, which is almost over here at the 180 degree mark, right? It's nearly there. It's at 150. Okay, so it's way over here. So the sine value over here, which is the y value, is what? 1/2. And the cosine value is square root 3 over 2, and it's negative. Yeah, so this is going to be negative. So I actually have 1/2 over negative square root 3 over 2, which simplifies pretty quickly to negative 1 over square root 3. And we can rationalize that. So to this. Now, in terms of working within the problem itself, it may not be helpful to actually have the rationalized form. So we'll look at that in a minute too. But before we get there, let's do tangent 3 pi over 4. That one's actually very friendly because what happens at 3 pi over 4? It's just 1. Well, it's negative 1 actually, right? But yeah, it's 1 because the sine value and the cosine value are the same except that one of them's negative. So this is actually negative 1, so I like that value real well. So for tangent right here, we'll go ahead and put the rationalized form in and work with that since we have it. So we have negative square root 3 over 3 plus negative 1. We'll write it that way. Over 1 minus, and we have, again, negative square root 3 over 3, and then this time it's times negative 1. I didn't allow myself more space. We'll just see how much space I can use up. I'm not sure. All right, so right now, okay, can I work across my page even though I would prefer us to keep going down because I'm going to run out of space? Okay. All right, so this is negative square root 3 over 3 minus 1 over 1, what's my sign? Is it? It's going to be minus. I got 3 negatives there, don't I? I do. 1 minus square root 3 over 3. Issue number 1, I've got a fraction within a fraction. Agreed? So this is where I'm going to do the same kind of thing we were doing with the identities. When I had a fraction within a fraction, I kind of looked at what would be my common denominator, and it would be 3, right, because I've got little denominators of 3. So the first thing I'm going to do is multiply by 3 over 3, because that's going to eliminate the double fractions. So when I do that, on the top, I'm going to get negative square root 3, because the denominator 3 is going to cancel, and I'm going to have minus 3. And then on the bottom, I'm going to have 3, and then again, minus square root 3. Are those pieces all okay? All right. However, every problem that we've worked thus far in trig, except for when we had variables underneath radicals, we didn't leave radicals in the denominator, right? We rationalized them, okay? So we need to do that here as well, but the rationalizing for this is a little different. We haven't done this yet, because that denominator has addition or subtraction in it, right? It's not just square root 3. It's 3 minus square root 3. So one of the things that that we talked about, but not in this sense, was a difference of squares the other day. Remember that? We're actually going to multiply by what would be the difference, and to make this a difference of squares. And it actually has a name. It's called the conjugate. So if you've heard that before, that's what we're doing. The conjugate of this denominator is going to be the same thing, but with the opposite sign. And we're going to do that because that will allow us to rationalize. Okay, so let me show you what happens with the denominator so you can sort of see why we did this. So I have 3 times 3, that's 9. And then the inside term would be 3 radical 3, but negative. And the outside term would be 3 radical 3 and positive, so those add to 0. And then my last term is square root 3 times square root of 3, which is 3, because it'd be square root of 9, right? And it's subtracted, because I have one positive and one negative. So no radicals are left. Now, the numerator doesn't work out so clean, right? I actually have to do it piece by piece. So I have negative 3 square root 3. I have, that's the first terms. My outside terms is negative square root of 3 times square root of 3, which would be negative 3. My inside terms would be negative 3 times 3, which would be negative 9. I'm almost done. I know we're out of time. I'm sorry, guys. And then I have negative 3 times square root of 3, which is negative 3 square root of 3. All right, we're almost there. So on the top, I can combine. I've got negative 12, and I've got negative 6 square root of 3. What's in my denominator? It is a 6. Sorry, I should be using the darker color to see easier. But this 6, you bet, this 6 is divisible by each of these terms individually, so I can actually divide them. And again, this is absolutely horrible because I don't have another slide. I should have prepared better. But they will simplify, so I actually have negative 2 minus square root 3. I'm off by negative from what my slide has on my notes here, so I'll have to figure out if I made an error. If I did, I'll fix it next time, okay? All right, what's that? I think it should be positive. I think I've got my signs off, but we'll fix it next time. This is the right idea, however, all right? We'll pause here.